How are stars formed? Stars, the luminous celestial bodies that dot the night sky, are formed through a fascinating and intricate process that spans millions of years. This journey begins within vast, cold, and dense regions of interstellar space known as molecular clouds, or stellar nurseries. To truly appreciate the formation of stars, we must delve into the key stages of this cosmic process, from the initial collapse of gas and dust to the eventual ignition of nuclear fusion. 1. The birthplace, molecular clouds. Molecular clouds are enormous regions of space filled with gas, primarily hydrogen, and dust particles. These clouds are often hundreds of light years wide and can contain enough material to form thousands of stars. Despite their size, they are incredibly sparse, with densities far lower than the best vacuums we can create on Earth. However, regions within these clouds are colder and denser, creating conditions conducive to star formation. In these cold environments, around 10 to 20 Kelvin, hydrogen molecules dominate, alongside trace amounts of helium and heavier elements. These clouds remain in equilibrium for most of their lifespans, with internal pressure balancing against gravitational forces. However, external triggers can disrupt this equilibrium, setting the stage for star formation. 2. Triggers for collapse. The process of star formation begins when a part of a molecular cloud collapses under its own gravity. This collapse can be triggered by various events, including nearby supernova explosions. The shock waves from exploding stars can compress parts of the molecular cloud. Galactic collisions. When galaxies collide, the gas and dust clouds can merge and collapse. Stellar winds or radiation pressure. Massive nearby stars can push against the cloud, causing it to compress. Gravitational instabilities. Over time, random fluctuations in density can lead to regions where gravity overwhelms internal pressure. Once the collapse begins, the affected region fragments into smaller clumps, each of which can potentially form one or more stars. 3. Formation of protostars. As the collapsing region contracts, it forms a dense core surrounded by an envelope of infalling material. This stage marks the birth of a protostar, a precursor to a fully formed star. The gravitational energy released during the collapse heats the core, causing it to emit infrared radiation. This heat is not yet sufficient for nuclear fusion but provides a glimpse into the early star's potential. During this stage, the protostar is often obscured by the surrounding dust and gas, making it difficult to observe directly. However, infrared telescopes can detect the heat emitted by the protostar, revealing its presence. 4. Accretion disk and jets. As the protostar continues to grow, it forms an accretion disk of gas and dust around it. This disk plays a critical role in feeding material to the growing star. The rotation of the protostar and the conservation of angular momentum cause the infalling material to spiral around the core, forming the disk. Simultaneously, powerful jets of material are ejected along the protostar's rotational axis. These jets help clear away excess material and regulate the growth of the forming star. Observing these jets provides valuable insights into the dynamics of early star formation. 5. Ignition of nuclear fusion. The key moment in a star's formation occurs when the temperature and pressure in the core become high enough to ignite nuclear fusion. For this to happen, the core temperature must reach approximately 10 million Kelvin. At this point, hydrogen nuclei, protons, begin fusing to form helium, releasing an enormous amount of energy in the process. This energy generates outward pressure that counterbalances the force of gravity, halting the collapse of the star. The star enters a stable phase known as the main sequence, where it will spend most of its life. The length of this phase depends on the star's mass, with massive stars burning their fuel quickly and smaller stars like the Sun enjoying longer, more stable lives. 6. Variability in star formation. Not all collapsing regions within molecular clouds successfully form stars. Some may fail to ignite nuclear fusion, resulting in brown dwarfs, often referred to as failed stars. These objects are too small to sustain fusion but may still emit faint light due to residual heat from their formation. On the other hand, particularly massive regions can form clusters of stars, leading to the birth of stellar groups or even massive star-forming regions like the Orion Nebula. 7. Star clusters and associations. Stars rarely form in isolation. Instead, they are born in groups called star clusters. These clusters can range from loose associations of a few stars to tightly bound groups of thousands. Over time, gravitational interactions and the movement of stars within the galaxy can cause these clusters to disperse, leaving behind individual stars scattered across the cosmos. 8. Role of stellar feedback. The formation of one star can influence the environment around it. Newly formed stars, particularly massive ones, emit intense radiation and stellar winds that can shape the surrounding molecular cloud. This process, known as stellar feedback, can trigger new star formation in some regions while inhibiting it in others. For example, the ultraviolet radiation from massive stars can ionize the surrounding gas, creating beautiful structures like the pillars of gas seen in regions like the Eagle Nebula, the pillars of creation. 9. Observing star formation. Modern astronomy provides several tools to observe and study star formation. Telescopes operating in the infrared, radio, and submillimeter wavelengths are particularly useful, as they can penetrate the dense dust clouds that obscure these processes in visible light. Space-based observatories like the James Webb Space Telescope, JWST, and ground-based facilities like the Atacama Large Millimeter, Submillimeter Array, ALMA, offer unprecedented insights into the early stages of star formation. 10. The larger picture. Star formation is a key process in the life cycle of the universe. It not only gives rise to stars but also influences the evolution of galaxies. Over time, stars produce heavier elements through nuclear fusion and supernova explosions, enriching the interstellar medium and enabling the formation of planets, moons, and even life. Each star, from the smallest red dwarf to the most massive blue giant, has its own unique journey, but all share a common origin in the cold, dark cradles of molecular clouds. Conclusion. The formation of stars is a testament to the dynamic and interconnected nature of the cosmos. It highlights how the simplest elements, hydrogen and helium, can combine under the force of gravity to create the complex and awe-inspiring structures that light up the universe. Understanding this process not only deepens our appreciation of the stars but also provides clues about the origins of our own sun, solar system, and the conditions that made life on Earth possible.